principally made of 4 different components: enamel, dentine, root cementum and tooth pulp. The tooth is mainly built of dentine, which is covered by enamel on the crown and by cementum on the root of the tooth. The enamel is, in addition, the hardest tissue of the body. The most important role of the pulp is during development to be the tooth-forming organ. At adult age, the pulp develops a sensory function which prevents the tooth from fracturing. A broken tooth can be of decisive importance to a wild animal. The pulp protects itself from invasion of microorganisms in the environment in a number of ways. One of them is to elevate the intrapulpal pressure. The dentine is latticed by a great number of channels called dentinal tubules, which extend from the pulp to the enamel or root surface. In some parts of the crown, the number of dentinal tubules can reach 20 to 40,000 per square millimeter. The dentinal tubules, in the shape of cones with side ramifications, measure the largest diameter close to the pulp, which make them extend over a larger surface deeper down in the dentine. Accordingly, a deep cavity is more permeable than a shallow. The dentine in the root of the tooth has less numerous tubules than the dentine in the crown of the tooth. During the lifespan of the tooth, the pulp continues to build dentine from the inside and reduces thereby its own living space. This is a normal process. In the peripheral portion of the pulp, a characteristic layer of odontoblast cells covers the dentine, and their cell processes stretch out in the dentinal tubules. In the immediate vicinity of them are bare nerve endings and blood vessels in a surrounding connective tissue. The odontoblasts produce predentine and exist as long as the tooth is alive. During damage in the dentine from either caries or other leakage of bacteria and their metabolites, irregularly built dentine is produced to protect the pulp from intrusion. The original odontoblasts are then exchanged with secondary odontoblasts. In the vicinity of the odontoblasts are nerve endings from the myelinated nerves of A type, while in the deeper layers of the pulp tissue, the unmyelinated C fibers will be found. Most of the free nerve endings are situated in the pulp of the crown. Less than 10% exist in the pulp of the root. Right below the layer of odontoblasts is a well-developed matrix of small blood vessels, which, among other things, provides the tissue with essential protective immunocells, nutrition, hormones, and other mediated substances. This is the quickest route of transport for necessary maintenance. The pulp has, however, a limited blood supply. 4 to 8 arterioles go through the apical foramen in every root. The hydrodynamic theory is a model that explains how icing sharp shooting pain is triggered by the fluid flow in the dentinal tubules. The nerve endings are excited by fast fluid flow in the dentinal tubules, and pain is evoked. Examples of stimulation which cause that kind of pain are fast variations of temperature, cold as well as heat. Also air blasting and substances causing osmosis, for instance sugar. The pressure in the pulp varies according to the blood pressure and follows the pulp condition. A damage of the enamel or the cementum will cause a higher pressure in the pulp, which creates an outgoing stream of fluid, which can dilute and neutralize excitants that tries to reach the pulp. Reduced pulpal pressure can also appear, which instead can cause the fluid on the dentinal surface to be aspirated towards the pulp. Inflammatory reactions can be seen early in the tissue under a carious attack in the dentine. This can also be seen under dentinal cracks, which can cause leakage of bacteria down to the pulp. Consequently, both the depth of the carious attack and the extent of permeability decide the proportions of the pulpal inflammation. If the distance between the carious attack and the pulp is more than 1 millimeter, the inflammatory response is considered mild. The early inflammation infiltrate consists almost exclusively of lymphocytes, plasma cells, and macrophages. In addition, small blood vessels and fibroblasts grow and collagen fibers are deposited in the tissue. Lymphatic vessels are important for the draining of inflammatory exudate. Fluid, leukocytes, cell products, plasma proteins, and fibrin are hereby transported from the scene of inflammation. If the distance to the pulp tissue falls below half a millimeter, the chronic inflammation is considered to pass to an acute phase. This happens when bacteria have invaded the reparative dentine under the lesion. In this situation, the secondary odontoblasts have been replaced by inflammatory cells. Dilatation of vessels occurs with increasing vascular permeability. Neutrophils and monocytes mobilize and find their way out in the surrounding tissue as an answer to chemotactic stimulation from the invading bacteria. Sometimes the concentration of neutrophils is so high that pus is created, as the neutrophils emits proteolytic enzymes which break down tissue cells. The area where the tissue is degraded gets a higher osmotic pressure than the surrounding tissue. The increasing difference in pressure, the emission of inflammatory mediators, reduced pH, and variations in ion balance raise the sensitivity in the adjacent sensory nerve endings, which then signal pain. This explains why an abscess in the pulp is often painful, and why draining gives a quick relief. As the carious lesion enlarges and an increasing number of bacteria enter the pulp, the defense of the pulp is overpowered, as the pulp has a limited blood flow capacity. When the need for additional neutrophils and other inflammatory elements at the bacterial wall front exceeds the transportation ability of the blood supply, the inflammatory response cannot gain more in force. The consequence is that the bacteria start to colonize the pulp, which inevitably leads to tissue destruction or necrosis of the pulp.